So we have seen water, or H2O storm, right, as an amphiprotic substance, meaning that it can donate a proton or accept a proton. And as a Bronsted-Lowry definition, that means it can act as an acid or a base. You might oftentimes see another term called amphoteric, which is interchangeable with amphiprotic. It simply means that it can act as an acid or a base. So one way to illustrate this clearly is to simply mix two water molecules together. So one water molecule is going to act as an acid, and one water molecule is going to act as a base. For Bronsted-Lowry definitions, that means that this acid is going to donate its H plus proton and be left with OH minus in solution, which is produced here. And this water molecule, the lone pairs on oxygen, is going to accept this proton from the acid here and form H3O plus. And H3O plus contributes to acidity of a solution, and of course OH minus contributes to basicity of a solution, based on, of course, the Bronsted-Lowry definitions we've seen thus far. So water having the ability to slightly ionize into H3O plus and OH minus is a process called autoionization of water. Auto comes from the fact that it's water mixing with itself, and ionization is, of course, producing ions. So when water mixes with itself, it produces these two ions, H3O plus and OH minus. And remember, we're talking about an equilibrium process. So that means we can quantify this entire process with equilibrium constant. Our equilibrium constant is always going to be K, right? And my K value, or my K based on concentration, is going to be my products divided by my reactants. As you can see, water here is liquids, and we already know the concentration of water is 55.5 molar. And so because of that, we can look at water as a pure liquid and it's going to stay constant. Therefore, we do not add it in our equilibrium calculations, right? And we know that from chapter 13. So we simply will have H3O plus as a product and OH minus equaling to our K value. Of course, you can divide this by 1, but we don't need to because we know that we do not include the liquids, okay? Now, this entire thing is also going to allow us to add another layer of information, which is basically taking our K value and giving it a specific name to relate to the autoionization of water, and that is Kw. And Kw is literally called the ion product constant for water, which is based on the products and the ions of water being mixed together because it's autoionizing, okay? And so Kw is equal to Kc, and so our Kw is still going to be equal to H3O plus and OH minus. Now, I said before, we know the overall concentration of water, right? And so we actually take this information and we're able to express K directly instead of having to use Q. So in chapter 13, we have Q and K, and sometimes we have to take that into consideration. But for our chapters here, our focus is always just going to specifically be equilibrium, so we are dealing with K. Now let's go further. We want to take our ionization equation here. Two water molecules is going to form H2O plus and OH minus, and we're going to build a simple Rice table. And we take our Kw value, our ion product constant, which we know is H3O plus times OH minus. After we fill out our Rice table here, we're going to be left with Kw is equal to x squared. And guess what, folks? There's people like other chemists in this world who've already done the work for us, and they found that at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the negative 14. So if I know that my Kw is equal to my H3O plus and OH minus concentration, and I know my Kw value here, I can solve for x. And if I solve for x, I'm therefore going to be solving for the concentration of H3O plus and OH minus, okay? So let's go ahead and do that. If we know that this is 1.0 times 10 to the negative 14, and this is x squared, of course, we're going to take the square of both sides. That means x is going to equal to 1.0 times 10 to the negative 7 molar. And that means that our H3O plus and our OH minus concentration is going to equal to 1.0 times 10 to the negative 7 molarity. So we're basically back to what we're understanding before. Let's consolidate. We started off with two water molecules mixing together in an autoionization process. They form H3O plus and OH minus. And this is our first indication to say, hey, now we can actually quantify these values here. And so what is that going to mean for us? If I can quantify H3O plus and OH minus, that means I have the ability to say whether or not a solution is going to be acidic or basic based on these values. And we haven't got that yet, but that's what we're getting to. Okay, folks? And so from this autoionization process, scientists found out that the Kw of water is equal to 1.0 times 10 to the negative 14. Of course, they also know the concentration of water, which is constant, and so that helped them get this value. Using a Rice table, we solve for X to show that at 25 degrees Celsius, okay, H3O plus concentration is equal to 1.0 times 10 to the negative 7 molar, and the OH minus concentration is equal to 1.0 times 10 to the negative 7 molar, all because water autoionizes. So what else happens as a result of this autoionization, right? Well, first, it's going to affect anything that's going to be aqueous, acid-base chemistry, mainly in two big ways, okay? The first way is that it gives us a relationship between the concentration of H3O plus and the concentration of OH minus, right? And the second way is that it helps us understand that each of these ions are actually always going to be present in aqueous systems, even if it's at tiny, tiny, minuscule amounts. No matter what, if I have an acidic solution, which a lot of H3O plus, there's still going to be some OH minus left. And if I have a basic solution with a lot of OH minus, there's still going to be some H2O plus left in the aqueous solution. And of course, we're at equilibrium, so that helps us understand that portion. So let's focus on the first way first. And here, one of the things that it does is it shows us a relationship between the concentration of H3O plus and OH minus. That is, if we increase H3O plus, we therefore are going to decrease OH minus. And of course, vice versa, if we decrease H3O plus, we therefore increase OH minus. And the way they tested that was through Le Chatelier's principle. They said, okay, I'm going to add some acid here. So you're like, okay, I have to add acid. If I'm adding a product, we know it's going to shift to the left, but also it's going to end up decreasing the OH minus as well, because I'm adding a bunch more of this particular product here. And I need to use the OH minus product as well to form the water molecules, because we are shifting to the left. It's almost like saying I'm increasing the concentration of a product, and so therefore I need to shift to the reactants to produce those more, right? And get everything back to equilibrium. So if I add a bunch of this acid, I'm therefore also going to decrease OH minus, because I have to take them both out of solution in order to form water. You can say the same thing in the reverse. If I add a bunch of OH minus here, then I'm therefore going to decrease H3O plus. I'm still going to be shifted to the left because I'm trying to get rid of products in order to produce more reactants, right? To get everything back to equilibrium. And so this is what they used in order to verify this particular pattern that they saw from the autoionization of water. Now let's get into the second thing, which is that both ions, H3O plus and OH minus, are present in all aqueous systems, no matter if they're acidic, neutral, or basic. So for example, in aqueous systems, scientists found, okay, if something is acidic, they're going to have a lot more H3O plus, way greater than OH minus, but there's still going to be some OH minus in solution. If they're neutral, then the concentration of H3O plus is equal to the concentration of OH minus. And if they're basic, then the concentration of H3O plus is much less than the concentration of OH minus, but it's still going to be hanging out in the solution. So all of these different properties that came out of water being able to mix with itself and autoionize is allowing us to kind of understand and rearrange that Kw expression. So we know that Kw is equal to H3O plus and OH minus, right? If we already know this value, which is a constant, then we can use that value to help us solve for any of these variables that we like. And so if something is super acidic, we see this relationship. If they're equal, we'll see a neutral relationship or at equilibrium. And then of course, if it's basic, we'll see more OH minus here. So what does that mean for us? That means that we can take our Kw amount or our Kw expression, okay, from equilibrium, and we can rearrange these variables to solve for whatever concentration we want. So if we want to solve for the concentration of H3O plus, if I already know my Kw value, I can base, and I already know my OH minus value, I can use these to solve for H3O plus. Same thing for OH minus. If I have my Kw value, which is 1.0 times 10 to the negative 14, that's never going to change, right? At 25 degrees Celsius, that's always going to be the same. It's something you could just go ahead and throw on your flashcard to remember. And if you have that value and you already have H3O plus value, you can solve for OH minus. And so rearranging these variables is going to be very important. That's one of the biggest things that comes out of this autoionization portion. Now let's take our summary and get into the Avengers compound for some examples. Okay, folks, we are back at the Avengers compound for examples. Remember, this is the time to create and build a strategy to approach problems. You never want to wait until the homework. Basically, try to create a strategy throughout the lectures and then layer on as you get to the homework. Because the goal is when you complete the problem with me, and then that helps you kind of think of a way to approach the problem, and then you want to go back and make it easier and figure out your own way. So by the time you get to the homework, you get to practice that, right? And then if you don't like what you did or came up with, you can change it before you get to the practice exam information. So it's almost just layering things slowly by shortly, okay? Now let's go ahead and read this question. It says, a research scientist adds a measured amount of HCl gas to pure water at 25 degrees Celsius. So we know a lot of the information we got from our previous portion of the video was that we're at 25 degrees Celsius. And it says it obtains a solution with the H3O plus concentration that equals to 3.0 times 10 to the negative 4 molar. It wants us to calculate the OH minus concentration and then answer the question, is the solution neutral, acidic, or basic? So first things first, let's go ahead and gather the information we can. What is essentially happening? We're taking something like HCl, and I think of HCl Hulk, which I know is acidic, and we're mixing it with water. So overall, if they're asking me if the solution neutral, acidic, or basic, I'm going to think acidic. I have to verify that, right, through the calculation, but I'm going to automatically think acidic because I'm adding acid to water here. And they're telling me that I have an H3O plus concentration, which is great here, of 3.0 times 10 to the negative 4 molar. They want us to know the OH minus concentration. Our way of connecting these is by one expression, which is our ion product constant equilibrium expression, and that's going to be that H3O plus and OH minus, when they're multiplied together, is equal to 1.0 times 10 to the negative 14, okay? Now, when I'm looking at this expression, I'm going to ask myself, okay, well, I have this number, which is 1.0 times 10 to the negative 14. No units attached, it's a constant. And I have this because it's given, 3.0 times 10 to the negative 4. I can go ahead and rearrange this expression to solve for OH minus. So if I want to solve for and isolate OH minus, then I'll say that my Kw value is equal to, or divided by my H3O plus concentration, and that is 1.0 times 10 to the negative 14 divided by 3.0 times 10 to the negative 4 molar. And as far as significant figures here, and of course everything's in parentheses for my calculator, I have two significant figures, and so my answer is going to be two significant figures. I have 3.3 times 10 to the negative 11 molarity. Now, we got our concentration of OH minus. That's the first part of the question. But they then want to say, is the solution neutral, acidic, or basic? And so our way of being able to describe if something is acidic, basic, or neutral is based on the amount or how large or small the concentrations of H3O plus and OH minus is, okay? So we have to basically compare our H3O plus and OH minus amounts. So H3O plus is 3.0 times 10 to the negative 4, while our OH minus is 3.3 times 10 to the negative 11. So therefore, our H3O plus concentration is greater than our OH minus concentration. And anytime we have that, we're dealing with an acidic solution. Okay, folks? So we have our concentration of 3.3 times 10 to the negative 11 molar. And then we have the fact that H3O plus is larger as far as magnitude. And so therefore, the solution is acidic. Okay, folks, move on to the next.